So that brings us over to the really tricky part, the part where we know we don't know how to do it yet. And that is interpreting the scans and turning them into a simulation. That would require computer vision. We need essentially to take those pictures and run them past software that figures out where are cell walls, which objects or synapses in these pictures, and then create a representation that there's a synapse between cell 4711 and 4712. And this synapse has the following properties. And this is important to do also because the storage requirements are enormous if you want to store the entire brain scanned at this resolution. Actually, that's going to be very problematic to do from a computer perspective for a very, very long time. So this leads to a rather unsettling conclusion. We're going to have to throw away the brain slice stuff because that's going to be wasted by the electron microscope. And then we have to throw away most of the data from the scan itself because we probably won't, at least in the early decades, won't have enough data to store it. So we better get that the processing part right. Otherwise, we're going to be losing brain location, and that's going to be so embarrassing to tell the relatives. So you can see really why we're going to need a lot of animal experiments long before that. Finally, the third part is about running the simulation. That's the one I'm least worried about. We just need big enough computers. So the very, very big question is Moore's law going to be continuing long enough? And we don't really know that. I think we can be pretty certain it's going to continue at least to 2016, and I'm pretty optimistic for a long time after that. But eventually it's going to slow down. That doesn't necessarily mean it's going out of the window, but it's just going to be more costly. But now we can put this together to actually make a kind of predictions. Because you might think in terms of what level of resolution we need. From that you can calculate how much computing power you're going to need for simulation. And then you can try calculating when is Moore's law going to hit that. Because that gives you the first date you could possibly do the brain emulation. So if you believe, for example, you need a ridiculous molecular simulation, then we can be pretty confident that Moore's law has to continue at this rate to 2090, I think, or something like that. The numbers are actually in my report. If you believe it's electrophysiology, then you get it in 2046. And now you can start thinking about it. Well, how much computing power will I actually buy here? 2046, that makes an assumption that you're using computing power for $1 million. If you have $1 billion, you get essentially get the same amount of computing power 10 years earlier. Which means that you can squeeze it. If you believe that somebody is going to want to make this as a huge project, then you can get at 2036. And that would be a human simulation. If you go for a smaller brain, like a mouse, that's going to be around between 10 and 20 years before that. So now we're down to 2026 or maybe even 2016. That's a really optimistic scenario, but I don't doubt anybody would want to spend $1 billion on running a mouse brain. And now, of course, we can debate about my estimation of computing power and so on. But you can kind of see how we can actually make a model. We can even start adding probability distributions about our assumptions and see roughly when we should start expecting to see something like this. And this, of course, leads to the most interesting questions that we can actually use this to get a rough sense of how far away are we. So the recent report about a cat brain size simulation, I haven't read the details yet, that's going to kind of help us calibrate, okay, how good are our simulations? And then we can start thinking about what other technologies are, how far away are we from scanning large volumes of data, for example. And right now the answer is we're not anywhere close to that. But there are a few companies starting up, like Todd Huffman's free scan. And they can actually scan an entire mouse brain, but they're doing it optical resolution. So you get a hard drive with 2 terabytes of mouse brain on it, which is already very, very, very cool. And I'm really hoping I can get a copy of that mouse brain. And so the real problem seems to be right now doing scan interpretation. And scan interpretation, that is, I think we need to work hard on that because it would be a nightmare scenario if we had scans that already stored in computer data banks and we have enough computing power, but we haven't done anything else. And then suddenly we get a breakthrough in interpreting scans, and then society won't have any time to actually handle the transition to a situation with copyable human capital. That's going to be very scary. It's going to be scary in a scenario in any case, if you just go in smoothly through this. So if you imagine that in 2026 we have a mouse simulation. That's cute. It's not very threatening, but it's very clear that in a few years we're going to go to a human one. That's going to perhaps create a big race for the human simulation. But at the same time, we actually have a bit of time to think about the problems and trying to set up a solution. That's much better than just getting a nasty surprise one morning.